Okay, so I'm going to be doing here a video solution for 6 on the free response without calc. Notice that it says without calc, and then I'm going to be bringing in some major calc ideas onto this thing, but again, you don't need calc to solve this, but for those of you that have taken a calc, you are going to recognize some major tips of the cap to calc ideas. So a force F is applied to this cart, which moves on a straight track. And here you can see that we have a force versus x graph. In this case, the force is a non-constant force. You can see that it goes up, then is constant for a couple meters, and then drops down to 0 and becomes a negative force after a while, which you imagine is slowing down the cart, and then it drops to 0 really quickly. And okay, so what's happening to the cart is easy to imagine. So the first thing is, how do we deal with force displacement graphs in order to figure out the work? So I'm just going to start with this idea that, that work is equal to FD. And also work is the change in energy of a system. It could be the change in potential, it could be the change in kinetic, but it's a change in energy. So notice that the force is a non-constant force. So this, if you're just trying to straight do FD, that might be a bit of a problem. So I'm going to zoom in here for a little bit and then just talk about in general the things that we can do with a problem like this. So I'm going to put again that work is equal to FD. So let's just imagine that we're trying to figure out the total work of this section right here, just that section for right now. So one of the ways we can do that is to take a look at the F times D. Now the problem again is that there's a non-constant force. So let's just imagine that we're going to break this into little pieces. So I'm just going to zoom in for a moment here on this little piece right here. All right, during this tiny little section right here. If we make this interval, or another way of saying it, if we make this little slice thin enough, then our approximation for F is going to be pretty good, right? Because the smaller this length here goes, for example, the less approximation you need and the more exact you'll get. So we could take a little slice across a really little small delta x, and since the work at that tiny little portion is FD, that's going to be the area right here for this little slice that we looked at. And now let's say we move up a little bit more in the on this line, and then we take the next little slice, which maybe we'll say is right here. And now we have a little higher force, another little delta x slice. And the FD, the work done during this tiny little section, this tiny little interval, will be this section here. And so you can imagine now that if we take enough slices of really, really small slices so that our force becomes more precise and less of an average, becomes more exact, then the total work done is really just the area in this space. In totality, right? The area is in this space. So the total work done on this object is really going to be the area under the force line, the force curve. And well, it's not a curve in this case, but under the force line. In an idea like this, where the lines are straight, that's really easy to do. It's geometry. But you can imagine, however, what if the force, looks something maybe sinusoidal like this? Well, then you would certainly this would be more of a calculus problem. But in this case, we don't need calculus because the line is straight lines. So if we could figure out the area here, let's say call this object 1, we'll call this object 2, and call this object 3. If we just figure out the total area, that will be the total work done during that section. Okay, so let's just figure it out real easy. For part 1, it's a triangle, so 1/2 base times height. So it's going to be 1/2 2 times 4, and that just looks like it's going to be 4 joules, right? So 4 joules right here. 4 joules of work was done during the interval or during the distance from 0 to 2 meters. This section right here, it looks really simple. It's just going to be 4 times 2, so this is going to be 8 joules of work done right there. 8 joules. 3, also not difficult. It's a triangle, so 1/2 base times height means that we're going to have 2 joules right here. So 2 joules here. Okay, so that takes care of this first part, and that is the total work done during this section, these different sections, and obviously it's for a total of 14 joules. 14 joules in totality. Now, the force has dropped to 0 right here, so there's no work being done here. Notice now that the F becomes negative in this case, and so the total work done right here is going to be 1/2 base times height. In this case, the base is 3, the height is 3, and so this is negative 4.5 joules of work being done right here. So the total work done, oh, and then of course it drops to 0 again right here. So the total work done on this cart all the way till the end of this scenario is going to be 14 plus 0 minus 4.5 plus 0 for a grand total of 9.5, positive 9.5 joules of work being done. Okay. So that's how we're going to start this. So A, calculate the work done when the cart moves from x equals 0 to x equals 5. Total work, that looks like just 14 joules. The change in kinetic energy during the time interval. Okay. If 14 joules of work were done and the thing was at rest initially, guess what? Now it has 14 joules of kinetic energy, right? It had 0 before, and now it's got 14 because you did 14 joules of work on it. What's the velocity of the cart at this moment? Well, all of this work is being converted into kinetic energy. So 14 equals 1/2 mv squared, which means 28 divided by 0.5 equals v squared. And so what is that, the square root of 50? So 50 to the 1/2 power, 7.07. So 7.07 meters per second. Okay, so that's the velocity of the cart right here, 7.07 meters per second. Okay. What's the work done by the force when the cart goes from 5 to 7? Well, that's 0. We already did that. A lot of these we did already. Is there any change in the kinetic energy during this interval? No. No work's being done. No work. Calculate the work done by the force when the cart goes from 7 to 10. From 7 to 10, it's negative 4.5 joules of work. The net work done in the car was the total 9.5 joules of positive work. 9.5 joules of positive work. And now what is the velocity of the cart at the end? Okay, so it was going 7.07 right here. We did some negative work with a negative force right there. So we would expect this final velocity to be less than 7.07 meters per second. In fact, if we get a number higher, we just immediately stop, hit ourselves in the head with something heavy to shake loose the cobwebs, and then we would do it again. So what's the velocity of the cart at 10? Well, again, it starts at rest, so it had no energy. All the work done, which is 9.5 joules, all that work is being converted to kinetic energy. So 9.5 equals 1/2, 0.5 v squared. So 19 divided by 0.5 equals v squared. So what is the square root of 38? 38. So 38 square roots, 6.16. That's not right. 9.5 times 2 is 19. Divided by 0.5 is 38. So 38 to the 1/2 power is 6.16. The reason I'm pausing is because I did this earlier with another student, and I did the exact same math, and I had a different number. So, did I do something wrong here? So 14, 9.5, yeah, that's okay. So we got 9.5 times a half, or divided by times 2, 19.5, that would be 19. 2 times 19 is 38. Square root of 38, 6.1. Yeah, it is what it is. Okay. So that is how we would do this question right here. I believe I had 6.9. Oh, you know what? I was thinking of problem 8. Okay, so we're okay. 6.16. Sorry about that.